So when you're writing electron configurations, the most common way is to use what's called spectroscopic or SPDF notation. And on the right-hand side there, this is an example of the electron configuration for hydrogen. So you use the NL notation. So hydrogen has N equals 1 and L equals 0, which is S, 1s. And then the superscript shows the number of electrons. So hydrogen has one electron, and earlier we saw the first electron, N equals 1, L equals 0, M sub L equals 0, M sub S equals plus 1/2. We always write the positive one first. That's one electron. That's the superscript right there. So that would be the SPDF notation for hydrogen, and that's what we'll use most of the time. There is, however, what's called orbital box notation, which can be helpful for magnetism. We'll talk about that later. So this is the spectroscopic notation for helium. Now, helium, if you remember from our conversation last chapter, helium is number 2 on the periodic table, which means 2 protons, and a neutral atom of helium would have 2 electrons. So the first electron would be N equals 1, L equals 0, M sub L equals 0, M sub S equals plus 1/2. And the second electron, N equals 1, L sub 0, M sub L equals 0, M sub S equals minus 1/2. So we would write that as a spin up, which is the green arrow, and then a red arrow spin down. And you can put the spin up first and the spin down later. That doesn't matter. So orbital box shows that you have one electron that's up and one electron that's down. And the number of arrows equals the number of electrons, which is the superscript right there. So spectroscopic and orbital box will be important as we go through, and we'll look at some examples as to how this works out. So when chemists talk about electrons in atoms, this is what they'll use. They'll use orbital box and or spectroscopic notation to figure out how this works. Lithium is number 3 on the periodic table. It has 3 protons. The atomic number is 3, but the neutral atom of lithium would have 3 electrons. So knowing that 1s is always filled in first, there would be an up and a down, and a third electron would be spin up in the 2s, because 2s is the next one to get filled in. Remember, these electrons always start at the bottom and kind of move their way up. Now, because this electron is by itself, a spin up without a spin down, lithium is paramagnetic, and that's the advantage of the orbital box. It does a great job showing it. But you could also write 1s2, 2s1, and that would be great. And make sure you put the 1 there, the superscript. Don't write just 1s2, 2s. That would be ambiguous as to the number of electrons. It's always 1s2, 2s1. Beryllium, right to the other side of lithium. Beryllium has 4 electrons total. That has the same electron configuration as lithium, but with 1 more electron. Now, to put an electron in the 2p box would be higher energy, so it's better to have a spin down in the 2s orbital. So beryllium would be 1s2, 2s2, 4 electrons total. And because every up electron has a down electron, beryllium is diamagnetic, not attracted to magnetic fields. So don't be thinking beryllium's going to do things around magnets. Boron is number 5, 1s2, 2s2 like the other two. This has 1 2p electron. Again, 2p would be the next one to get filled in. Spin up arrow before down arrows. 1 unpaired electron would be paramagnetic. So again, 1s2, 2s2, 2p1 is one way to say it, or you could write orbital box, 1s filled 2, 2s filled 2, 2p1. Both are great. Now, when you get to carbon, something special happens, and I want to talk about it. So carbon has 1 more electron than beryllium. Thanks for playing. It has 1 more electron than boron, so it has 6 total electrons. It's going to be 1s2, 2s2, 2p2, but you have a choice where the 6th electron goes, because you could put it in the same box as the 2p1, so you'd have an up and a down together. But what scientists have found, what is specifically Hund found, is that you have a lower energy configuration when electrons are placed in their own orbitals first. So you never see a 1s2, 2s2, 2p2 where both electrons are in the same box. box in the same orbital. You always see them in separate boxes first. So Hund's rule just says that you always want to place electrons in their own orbitals first as long as possible. After a while, you have to start pairing up, but at first you want to keep them far apart. And remember, these electrons are all negative, and negative charges repel each other, so it makes sense to try and keep them as far apart from each other as you can. Hund's rule is exactly what that means. Just put them each other. So this is paramagnetic. It would be diamagnetic if you paired it up. We would also say that carbon with 2 unpaired electrons is more paramagnetic than boron with 1 unpaired electron. The more unpaired electrons you have, the more paramagnetic, the more interested in magnetic fields it is. Nitrogen would have 1 more electron than carbon. We're going to use Hund's rule, put each electron in its own box. We're not going to pair anything up. This is the most paramagnetic element we've seen so far. 3 unpaired electrons, 1s2, 2s2, 2p3. Oxygen, 1 more electron than nitrogen. Now, oxygen has an electron that has to go somewhere. It's higher energy to go to 3s, so now we're going to start pairing it. So with oxygen, we start pairing electrons up. So oxygen would only have 2 unpaired electrons, as it turns out, 1s2, 2s2, 2p4. Fluorine, with 1 more electron than oxygen, will pair up another one of those paramagnetic atoms, 1s2, 2s2, 2p5, but it's also paramagnetic. Again, nitrogen would be considered most paramagnetic because it has the most unpaired electrons. 3 unpaired is more than 2, which is more than 1, etc., etc. When you get to neon, you have 10 total electrons. That's 1s2, 2s2, 2p6. And at this point, all of the electrons are paired up. Everything has a pair. So neon is definitely diamagnetic. All right, no interest in magnetic fields. So this is now the end of the second period, which periods go left to right on the periodic table. So at this point, everything is paired up. So notice that for all of the elements we've seen so far, helium, number 2, beryllium, number 4, and neon, number 10, those are the only ones that were diamagnetic. Most of the elements on the periodic table are considered to be paramagnetic because they have 1 or more unpaired electrons. But also notice at the end of the p orbitals there, everything is diamagnetic. Same thing at the end of the s orbitals there, everything is diamagnetic. When you get past neon, a lot of times chemists will use what's called noble gas notation or core notation. And so, for example, for aluminum, which is 3 more electrons than neon, you would have 1s2, 2s2, 2p6, 3s2, 3p1. And that's a lot of syllables, obviously. So what chemists will use is they'll go backwards to the nearest noble gas and put it in square brackets. So the most recent noble gas was neon, so you'd write neon, Ne, in square brackets, and then whatever is left. So neon 3s2, 3p1, which is kind of cool. This is what they call core notation, and it's pretty awesome. So all of the group 3a elements are going to have this kind of notation. They'll have some kind of core, a noble gas core, and they'll have, depending on their period number, they'll have ns2, np1 electrons. Some of them will have Ds. We'll talk about that in a second, but it's kind of cool. And the reason why these all have the same pattern is why they all kind of react the same. And this is something we'll build on in later lectures too. Phosphorus has a total of 15 electrons. It's group 5a, 1s2, 2s2, 2p6, 3s2, 3p3, which is a lot of words, or you could just say neon 3s2, 3p3, and that's why scientists like it. So this is another example. Everything in group 5a has an ns2, np3 outer core. Some of them have the Ds. We'll talk about that later. But anyway, it is kind of neat, and this is why everything in the same group kind of reacts the same. So in the last chapter, I said you should really know groups 1a and 2a, alkali and alkaline earth metals, as well as groups 7a and 8a, which were halogens and noble gases. Those groups have very similar reactivity, and that can be kind of helpful when you're a chemist. Chlorine is one of the halogens. It's in group 7a. And the question is, what is the electron configuration for it? So 17 electrons is what we're going to try and put here. So let's say that you are totally confused by what this is all working out. But you know that chlorine is number 17. Well, one way to answer questions like this, and it's not foolproof, but one way is to literally count the number of subscript numbers. So as an example of that, let's look at answer C. C has 1s2, 2s2, 2p5. And if you count those superscripts, that's 2 plus 2 plus 5. That's a total of 9 electrons. And we want a system with chlorine that has 17 electrons, so that's not enough electrons. So answer C is not correct. That's actually the electron configuration for fluorine, if you remember earlier. So if you look at these different superscript numbers, all of them are not quite 17 except for B. And B, if you count that up, 2 plus 2 plus 6, that's 10, plus 2 plus 5, 7 more, 10 plus 7, 17 total electrons. So that does work sometimes. Now, it's not perfect, all right, but that is one way that you can do these kind of configurations. So A right there would have a total of 12 electrons, that's magnesium. D has a total of 18 electrons, that's argon. E, I believe, has a total of 20, which is calcium. So you get the idea here how this works, but it's a cool little tool that can help you out sometimes. Now, main group elements are elements in groups 1A and 2A on the far left, and groups 5A through 8A on the far right. Now, this periodic table is using 13 through 18. That's what they call the international version of the periodic table, which can be helpful. However, for our purposes, think of boron in group 13 there as being 3A, and helium and neon are officially groups 8A on the periodic table. But anyway, main group metals are different than transition metals, which are in the middle, as well as lanthanides and actinides, which are the two rows there on the bottom. And transition metals are basically the ones that have d orbitals, and lanthanides and actinides are going to use pink orbitals. Lanthanides and actinides are going to use f orbitals. So this is a nice way to kind of think about it. The s's are the two columns on the left-hand side in helium. The p's are the 6 columns on the right, not including helium. The transition metals are the groups in the middle, and those are essentially d electrons, while the lanthanides and actinides at the bottoms are f orbitals. When it comes to transition metals, almost all of them have some kind of noble gas core, NSX, N-1 dy, all right? And I'm sure that's as clear as mud, so we'll show some examples of that here in a little bit. Likewise, lanthanides and actinides have some kind of core, NSX electrons, N-1 dy, so some d electrons, and N-2 Fz orbitals, all right, but with exceptions. So again, transition metals, kind of the middle group there, chromium, iron, those kind of things, copper, very, very common. Lanthanides and actinides can be things like uranium and cerium, plutonium. So these are things that we definitely know about and hear about, and it would be cool to talk about their electron configurations. So these are just some examples of how this works. So potassium and calcium, I think, are probably going to start looking more familiar to you. They both have an argon core and a 4s1 or 4s2 configuration, no problem. Scantium is number 21 on the periodic table. So it has the same electron configuration of calcium, but with a 3d1. So earlier with transition metals, it said N-1 d electrons. That's because you're in the fourth period. 4 minus 1 is 3. So that starts the 3d electrons. Titanium, one more electron than scantium, would be 3d2. Vanadium would be 3d3. But look what happens when you get to chromium, because chromium would have one more electron than vanadium. And for whatever reason, electrons jump ship from the s to the d. So instead of chromium being a 4s2 3d4, the actual configuration is 4s1 3d5. And this is one of the exceptions to the so-called N plus L rule. Now, when you get to manganese, it goes right back to the old orbital, to the old pattern, 4s2, 3d5, etc., etc. Copper is also an exception. Instead of 4s2, 3d9, it's 4s1, 3d10. So there are some exceptions to these electron filling rules on the periodic table. The N plus L rule is breaking down. So this is an important part to talk about, because in science, not everything is known. Those silly cloud speeches that Lord Kelvin gave in 1900 are so wrong. So N plus L rule works really well most of the time, but not all of the time. So maybe one day this is something that one of you will work on, and I'll have a better description as to how to describe electrons going in. So just realize N plus L does not work perfectly. There are these anomalies. And again, one day maybe one of you can figure out a better theory, and I can talk about it instead of these weird exceptions to the N plus L rule. If you want to form anions, negative ions, or positive cations, positive ions, you can do that with these two. And I'm going to show some examples here with orbital box. So anions, negative ions, you would literally just add the additional electrons using normal rules. So on the left-hand side here, we have phosphorus. And on the right-hand side here, we have the phosphorus minus 3 ion, phosphide ion. Phosphide has 3 more electrons than phosphorus. And so you can see what happens here. They just filled in those 3 paramagnetic boxes and made them all diamagnetic. So phosphide has a neon core, 3s2, 3p6, or an argon core. So to make an anion, you just fill in the lowest unoccupied spots to figure out what the electron configuration is. No problem. Cations, positive ions, are a little bit different, but a similar idea. When you want to make a positive ion, you remove 1 or more electrons from the subshells of highest N or highest N plus L. And I'll talk about what that means here in a little bit. Now, aluminum likes to make aluminum plus 3. So that's removing 3 electrons. So highest N or highest N plus L, we're going to take them from N equals 3 because that's higher than the 1s2, 2s2, 2p6, the N equals 1 and N equals 2 of the lower ones. So we're going to take away the 3s2, 3p1 electrons to make 3p0, if you will, and 3s0. We're going to be left with 1s2, 2s2, 2p6. So aluminum 3 plus has a neon core. Now, what we would do here is we would take away the 3p1 first, technically, and then we take away the 3s2 electrons after that. But it doesn't make a difference because we're taking away 3 electrons. The end result, aluminum 3 plus, will have a neon core. So here's an example of a question you might see. The electron configuration 1s2, 2s2, 2p6 represents which ions and or atoms? And we've got here the sodium ion, the oxide ion, the magnesium 2 plus ion, the neon atom, or all the above. So one thing you could start with here is adding up the superscripts like we talked about. So 2 plus 2 plus 6, those superscripts represents 10. So that means neon is going to have a 1s2, 2s2, 2p6, definitely. However, sodium has a total of 11 electrons. And if you take away one of the electrons to make it positive 1, 11 minus 1 is going to give it 10 electrons. And 10 electrons is 1s2, 2s2, 2p6. Sodium plus 1 is also going to be this configuration. Same thing with magnesium. Magnesium normally has 12 electrons. Magnesium 2 plus would be 2 less than that. That's going to take away from the 3s electron shell and subshell. So that means magnesium 2 plus with 10 electrons also would have 1s2, 2s2, 2p6. And oxide, O minus 2, is going to be oxygen, 1s2, 2s2, 2p4, with 2 extra electrons. And if you add electrons, you'll add the 2 extra electrons to the 2 spaces that were paramagnetic before. We showed that earlier. oxide also has a 1s2, 2s2, 2p6 electron configuration. So all of these are 1s2, 2s2, 2p6. And sometimes in lecture, I'll talk about how noble gases are like the cool kids in the back of the bus. And everybody in the bus wants to be like the cool kids in the back. The atoms themselves will often obtain a noble gas notation to be like the cool kids. So sodium loses an electron to become sodium plus because it's going to have the neon core. Oxygen wants to gain 2 electrons to be like neon, have its same electron configuration, etc., etc. It's a juvenile thing, but there is stability in having electrons equal to one of the noble gas configurations. If you have a transition metal, there's a little bit of a twist here I want to talk about. When you make a cation, you remove the electrons first from Ns and then any N-1 electrons. So highest N first, then highest N plus L. So with transition metals, 4s gets filled in before 3d. If you look back at the Aufbau diagram, 4s gets filled in before 3d, 4p after that, etc., etc. So if you're making iron 2 plus, you need to remove the electrons from the highest N, 4, before you do the N equals 3. So iron plus 2 still has 3d6. Those electrons haven't changed. And why that's kind of weird is that the 3d6 were the last electrons in, if you fill them in that way, but they're not necessarily the last electrons out, because 4 is higher than 3. 4s electrons come out before 3d. Now, if you make iron plus 3, then you start whittling away at the 3d electrons. So iron plus 3 would have a 3d5 configuration, etc., etc. So you always want to remove electrons from the highest N first when making cations. And spoiler alert, this is big time important for transition metals, lanthanides and actinides, because you almost always remove those Ns2 electrons first before you remove any Ds or Fs. Magnetism, super important, also important when it comes to transition metals. And again, you can totally figure this out. So some of them will be paramagnetic, some of them will be diamagnetic. Zinc 2 plus, when you figure out zinc has 4s2, but you take away those 4s electrons first. Zinc 2 plus, every up has a down in the d orbitals, it's going to be diamagnetic. But most of the transition metals will be paramagnetic when they're ionic. You can see that some of them have more unpaired electrons than others. Again, more unpaired electrons means more paramagnetic, and less unpaired electrons means less paramagnetic. So manganese 2 plus would be more paramagnetic with 5 unpaired electrons than iron plus 2 with only 4 unpaired electrons. So here's a question you might see. It says, which ion corresponds to the following electron configuration? Now, notice here that this has an argon core, an empty 4s box, and 3d electrons. And if you count the up and the down arrows, there are 7 electrons there. So 3d7, okay? So knowing that it has, first of all, an argon core, it cannot be answer B, because rhodium is not in the argon set. It would be the next one down. It would have a krypton core. So B is out. All right. So if it has a 3d7 and no 4s, at the very least, it had to lose 2 electrons. So be positive 2. So if you look on the periodic table and you start with scantium, that would be 3d1. Right next door would be titanium, 3d2. And if you go over to 3d7, you should find cobalt. So cobalt plus 2 has an argon 3d7 configuration. So on the right-hand side there, I have the neutral atom electron configuration on the left and what it would be on the right-hand side. Remember, all the s's go out first. So iron plus 3, the 4s2 electrons are out first, and you'd lose 1 more electron to make 3d5. And then the same thing like for nickel there on the bottom, you'd have argon 4s2 3d8. First 2 electrons out are 4s, so nickel 2 plus would be argon 3d8. But cobalt plus 2 would be argon 3d7, and that's what we're looking for, which is kind of cool.